So we're going to flip our paper over and we're going to talk about the tangent line. So what we just saw in 12.2, that practice problem, that's where we're finding the tangent to a point. So notice how we let x equal 3. That's called finding the tangent at a point, okay?
What is the tangent?
The tangent is, I'm going to tell you in a second. Yeah. So the goal is to understand what is a tangent, basically. And so what is a tangent? Use the tangent to approximate the slope at a graph at a given point. And that's because at this point, most of our graphs have curves on them, right? They're not just straight linear situations. So we're trying to find what is the slope, what is the change, the rate of change from this point specifically on the graph, okay? All right, so tangent line to a graph. What we did in 12.2, that practice 4 was us finding the tangent line at x equals 4. Okay, yes. We're good.
Okay.
It's all coming. It's all coming to you. It's all coming.
Sorry.
All right. The tangent line to the graph. So if you're given the point x1 comma y1, the line that best approximates the slope of the graph at that point. So a tangent line is the slope approximately at that point. Do we all know what slope is? Rise over run. Yes, but it's our rate of change, right? It's how is something changing at this given time. How did this plant grow? Okay, it's more generalized at a specific point. How did that change? Okay. To determine the rate at which a graph rises or falls at a single point, you can find the slope of the tangent line at that point. Okay. So again, what is the tangent?
Slope.
The slope of a graph
At
at
any given point.
a given point, a specific point, right? Okay, that's the key thing. It's at a specific point. Okay. So we learned how to find slope a long time ago, I hope, right? In general form, we're good there. And that's good. That's easy and breezy with linear functions. However, notice, have you ever had to find the slope of a quadratic or of a parabola? No, you have not, right? But you can find the slope of a quadratic at specific points, but there is no slope to the quadratic as a whole. There's a slope to each point, but not the quadratic as a whole. Okay. Because depending on the situation, it can be at this specific time, what was the rate of change happening? At this specific time, what was the rate of change happening?
But it's not moving.
The point, what you guys fail to realize is you think that the graph represents a motion. The graph doesn't represent the motion. The graph represents the actions that took place during that time window or over a space.
How do you find it?
So
Was there a top that way?
that's your introduction to slopes. Yeah.
If you find the slope between here and here, and you do like this is gonna find that though, right?
Yes, but you're finding the slope between 2 points. Here you're finding the slope at 1 point.
So it's not even gonna find, oh.
Yeah, that's the trick, okay? So like Alexis pointed out, in the past, we've always found the slope between 2 points, right? Yes, y2 minus y1 over x2 minus x1, right? We're now moving from that because we're going to just be analyzing specific change at a specific point, okay? And that's going to lead us to our instantaneous rate of change in calculus, exactly, okay? All right, so these are different ways that you can analyze the slope. So if you look here, this point has a positive slope, right? This point has and this point has a what? What's the word? Starts with a C. Constant. It's a constant slope, right? Okay. Do we see that? So at our maximums and our minimums of our graphs, we're going to have what? Constant. That they're going to have a constant slope. Okay. All right. Which means that their slope is going to be 0. 0. Okay. With this, you also can then find the slope around a circle because it's at a specific point.
This is circle slope equal the same thing.
Same way that we're doing it, same process. Yep.
No way, there's a slope there and you would slope there.
No, may not. All right. So slope of a graph. Here we go. When you are drawing, I wouldn't either. This is the very formal definition. To find the slope at a graph on a graph, you draw a tangent line to the graph. So to approximate it, and then you would think you can just count out the rise over the run, right? But that change is so small that it may not be easy, okay? The best way that we're going to calculate it is by using our difference quotient. I'm going to go through all that, blah, 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 blah. Okay? In the past, key thing here is we're going to do change in y over change in x, but we can't directly find that. Okay? So if I'm at f of x equals x squared, and you want to see the tangent line at 1, 1. Right? How can I approximate that? Well, if I plug this in, I'm looking for what's the change in my y over the change in my x. I thought I graphed it. Okay, why? Because the tangent line at 0.11 has a slope of about 2.
Oh, it's the one from my other one.
Yeah, from the other one, yeah. This one,
Oh.
sorry. This is us approximating. Remember I said initially we learn by counting, rise over run. So when I count here, I can see, okay, well, it looks like the slope of this line, it rises 2 and falls 1, right?
It could be 1, and you just go from 0 to 1.
Exactly. That's why this is just a approximation.
Do it the other way?
Yeah, we're gonna do it formally, but if you're just kind of gauging to see where you're at, you can approximate it.
I mean,
So-
like where to start, like where to go.
So when you are drawing it, you want to create it where it's only, this line is only touching this point. So that's what makes it really hard, is because you're like, okay, I only want the line here to touch this point and then continue. And then you can find on this line, it starts here and ends here. So I'm roughly saying I rise to 3 and I ran over to 2, right? So the key thing is, it's only touching one point of the graph. Okay, that's why we call this a approximation, right? Because it's not gonna always be that accurate. Yes? Okay.
Should we draw that?
No. All right, so we can approximate it, we can do that. So this is what the approximation would look like. And it goes, cool, yay, we approximate it. Now, what if I really want to find it, right? What if I really want to calculate the slope? What do I do? All right. Here we go, the secant line. So we're gonna find the secant line. A line through the point of tangency and a second point on the graph, okay? And then difference quotient is where it comes back into play. So we're gonna be using our difference quotient. That's the f of x plus h minus f of x divided by h. And so what someone discovered is that if you want to find the exact value for your tangent at that point, you're actually going to be using the limit, okay, of your difference quotient. And then you're going to plug in that value to find it, okay? So our limit, this is the main gist of it. Is there a highlighter? Yes.
That's what we need to write.
Yeah. And it's going to be at. Okay. And that's going to be how we no longer are just approximating, but we're actually finding. Okay, after you write this down, then we're going to do one. I just looked at your notes and it should have the example 1. Yes? Yes.
Stop looking at me so freaky. No, you're always looking. No, you look at me. Every time I look up, you're already staring. No, you were just staring when I looked up. It's not about this point. Every time I'm in here.
Yeah, in here feels like no one's here.
Yeah, I know.
Did you write down what was highlighted?
Miss Jones, I did.
We're good? All right, so how does this benefit us? Well, it gives us a point to use as, so that we were kind of using our rise over run still. However, now our rise is going to be this, our f of x plus h minus f of x, and our run is going to be our h. And that's how that limit comes into play. This is going to be our rise, this is going to be our run, okay? All right, so this is just further explanation of what's happening. You can go back through and talk about it. And then this is just other views of where it could lie. The closer you are, the better. And then the closer you get to it, closer, then you're going to end up at your tangent line, okay? All right, so main thing here, we wrote it down. We're going to use it, and here we go. So we have the limit process to find the slope of the graph, f of x equals x squared plus 5 at the point 3, negative 1. The main thing here is your x is what? 3. Okay, the y doesn't matter, only the x. The y can't help us. All right, so we're using our f of x plus h minus f of x over h. I forgot to write limit, guys. I'm sorry. Can y'all tell that says h goes to 0?
Yeah, no, but.
Lim, you get what I'm going. You see it. All right, so we're looking for specifically at x equals 3, right? Agree? All right, so when I'm evaluating this, we'll already know the function value, right? So we won't have to plug it in when we get to this. We're just going to be plugging it in for here at x plus h. So I'm going to write it all out. So we have f, and what is our x? 3. So 3 plus h minus f of 3 all over h.
I thought you would just say. Sorry.
Let's try this class, Sam.
Yeah, and your only chance of finding it. Always talking about.
Sam, we don't like you.
No, we're not.
Yeah, we have to take days off because we have to wait for your.
Okay.
We have to wait.
We have
You're Sam.
all right. Hey, focus.
The collective of words has is part of the collective.
You don't get -1. Yeah. Why did it put -1 here?
Should be in 6th grade.
Also, you have like 5 That's over here.
I don't think that's gonna be right. That -1, I'm not sure where that -1 came from. Yeah. No.
Happy party. Happy party. You put up a different number. That's lame. Hey, but you know, like,
Let me say the two people bring their part of. Wait, come back? Come back? Hey,
You can make it. Oh, you might have that.